All right, I think I'm gonna get started. So, hey everyone. So today's gonna be a kind of a different episode. So I'm gonna talk about semiconductors and really like a few aspects of it. Like maybe we'll touch on some technology aspects, but really what I want you to come out from this is sort of like the complexity of this space, as in like one, there's so many players involved, there's so many technologies involved, and also just from a geopolitical perspective, like the stuff gets really crazy. Like it gets at the heart of some of the tensions between like the US and China. So we're going to be talking about them and sort of like where the battlegrounds are, like which countries, which companies are sort of the issue in this. And so, and also like given that like I would imagine a lot of you are interested in machine learning, I do want to make sure that I spend an adequate amount of time giving you some perspective as to how this influences like ML accelerators. So we'll talk about Nvidia, and given that it just came out, like maybe we'll talk about Dojo a bit, like Tesla's Dojo, see like how it's different or how you should go about thinking about it, because it's really easy to do what I call flops porn, or you can say like, oh, like, we have so many flops, but in and of itself, that's not necessarily that useful of a metric. Like you need a bit more information or data to figure to sort of really make sense of it. So let's just start, I guess. I know it's gonna be a lot. You're gonna do lots of googling as well, because one thing, like I had one of my colleagues at GraphCore, like Brian Yang, he used to say that there's no such thing as a full stack hardware engineer. So keep that in mind. Like I think in machine learning, we sort of have this fortune that you just need to know how supervised learning works, and you can do 80% of stuff, and you can pretend like you're a galaxy brain. But this is like legit complicated. Like the world of like bits doesn't necessarily care about your abstractions. Like it is what it is. We're dealing with fundamental physics problems and social problems as well when it deals with countries. So yeah, keep that in mind. And with that said, I think we can just go ahead and get started. All right. So first off, like just in terms of terminology, uh, so, so a semiconductor is basically just means like a material that can conduct electricity efficiently. So they're typically made of a few materials. So like silicon and germanium, as far as I know, and I think gallium arsenide is a bit newer. And so is cadmium selenide, although I don't even know what that is. Uh, but just suffice to say, here, let me zoom in a bit. That these are all these are all like physical things that you have to mine in the real world, right? And so a natural question is like, well, like where are these mined, right? So let's say if you were to look at silicon deposits, um, in the world, you can see that there's about like 7,000 tons produced in the world every year. And more than half of that is all in China. And then you have 600 tons in Russia, there's Norway. But you can sort of see how this is a long tail, right? And so this is a tension point, right? So you have something like computers, which everyone needs in the world. Like, it's extremely unlikely that we'll stop using computers anytime soon. But then most of the supply is in the hands of a single country, right? And so, is this true? Like, let's say for cadmium, for example, is that true? Let's try germanium supply. Nope. Germanium supply by country. Yeah, so also China. It's about 60% of the total production. Okay, so maybe the other ones are different, right? So let's try gallium arsenide, right? What about gallium arsenide supply by country? Okay, interesting. So it's in the US, right? So if 95% of it is consumed, I see. Produces. Oh, okay. 95%. Okay. And so this is used in high frequency radio waves and 5G base stations. And it's one of the 35 elements that the US government calls a national security concern, right? And so for me at least, when I started to learn a bit more about semiconductors, like the trade war started to make a lot more sense. Like sure, there's some stuff that are relevant, but this is sort of like the one thing that's inescapable that we all need. Um, So that's in terms of mining, right? But let me sort of give you a holistic overview of sort of what's involved in this space, right? Because it's not just about mining, right? So first off, you have like the mining, right? So this is like getting resource like so getting resources that you can then basically put in into like you would think, okay, well, let's say you have a design, and then you have like some mining facilities, you have the manufacturing facilities, and then you have a packaging uh, plus testing, right? So sort of, and then of course there's other stuff, right? There's like the software and all that stuff and compilers, but let's ignore that part for a second. So in terms of like mining, so we just saw, okay, well, most of these are countries in China. I also like when last I looked, like there's a couple like large deposits in countries like Russia and Kazakhstan. Um, the design is, think of it like these are the companies that you've heard of. So this would be like Nvidia, right? ARM. So these are the companies that design chips. So Nvidia, famous for GPUs, popular for. Okay, so let's talk about Nvidia. I know we are gonna digress a lot, unfortunately, in this talk, but it's okay. I think I just want to give you a sense of the complexity of the space, right? So first off, like let's just put things in perspective, right? Let's look at the Nvidia stock price. So this is an exponential curve for a publicly traded company that was like worth close to nothing until 2016, and then all of a sudden like exploded in popularity. It did have like a big boom and bust around 2018, so it did have a serious crash. But there were three things that sort of explain this growth, right? So one is deep learning, right? So basically, I've said many times here that deep learning is basically like matmols. GPUs are matmol machines, right? The other is gaming, although this still represents a small fraction of the the total size of the space, because you can only have so many gamers in the world, right? Like this is like this scales basically to a certain set number of. It's still a lot, right? Like if every person on the planet buys a GPU, like that's still a great business. But it's not like deep learning where you could just potentially have like millions of machines or whatever. It sort of doesn't matter how many. There's no upper bound on number of humans or anything like that. And the last is like cryptocurrencies. And so this is basically for basic. Historically, like for Bitcoin, for example, they used to use GPUs to mine it, but right now they've moved to like ASICs, which sort of remove all the non-Bitcoin stuff away from it. And I think Ethereum is doing the same thing, and probably other cryptos will do the same as they get more popular. But if they're not, then it sort of doesn't rationalize. So basically, the only reason why someone would need specialized hardware is if really the use case is so valuable and there's just nothing else that does this. So we also said, okay, so this is NVIDIA in terms of use cases. So all three of those use cases are exploding, right? Like all of these are becoming more popular. Like let's say with gaming, like let's say COVID accelerates that. But also in general, like lots of younger people, I don't think like care too much about movies anymore or plays or whatever. So this just becomes a new kind of entertainment. And cryptocurrency is like, who knows? Like I mean, I'm personally bullish on Bitcoin, but at this point, like I'm not even sure, so I'm not gonna comment on it. So suffice to say that all of these things contribute to like a huge appreciation in the Nvidia stock price. But really, when Nvidia is comparing itself against its competitors, right? So you have all sorts of companies like Tenstorrent and now Dojo, and Intel I think is doing their own GPUs. ARM has their own. Sorry, not ARM. AMD has their own GPUs. So all companies have their own GPUs. So how do they compare themselves basically? So how do you evaluate uh, new hardware, right? So the first thing to keep in mind is that you're really only like when you're evaluating something, that there's a couple of benchmarks that really matter. Right. So this is sort of in deep learning, for example, this would be like your ResNets. So this would be your BERT. Right. And what you want to show is some good performance on single node, but also some story as how do you scale out, right? So basically, let's say you want to, have like petabyte models or whatever. How do you do that? So you distribute data parallel. You just shard one model. Like How easy is model parallelism to do, etc. So this is what I just call like basically, but even before we get there, so this is sort of like what I would call model level performance. But then there's like flops, basically the floating point operations per second. So like let's say the machine does I don't know, like 1 petaflops uh, per second. So that means that it does 10 to the 15 floating point operations per second, right? But that doesn't necessarily mean float 64 or float 32, right? It could be, well, maybe it's float 16 or maybe it's float 8, like, who knows, right? But essentially, this is more of a this is more of a use case that depends on your application, right? So if in machine learning turns out precision doesn't really matter all that much, that means that you should be able to bring it down and potentially get like higher flops because it's like physically the units that will do floating point 16 will just be smaller, they'll consume less power. So just think of it as a like basically as long as the application people are okay with it, this is something that you can do in hardware, right? So, but although famously enough, I'm assuming if any of you have used GPUs before, one thing you may have really struggled with is utilization, right? So basically, you're like, okay, I'm using a GPU, but then like 15% utilization, right? And you're like, well, what the hell is going on, right? And so what you do is like you'll increase the batch size, and then at some point the utilization goes up to 100%. But essentially, what this is talking about is actually your like I/O bandwidth, like so your memory bandwidth, as in like how much data can you send to the accelerator? So data rate to accelerator. So the idea is that it doesn't matter how fast you are if you can't ship data to the machine fast enough, then it doesn't really matter. So this is a trade-off. So ideally, you want like both of those numbers to be high, but obviously there's you know, like if it's just really fast, then maybe you could load like the same amount of data that you're doing the same computation on. I don't know how useful that is. Or you have lots of memory bandwidth, so you can send lots of like large batch sizes. You can do training really fast, etc. And then you just need to make sure that your flops basically keep up. So another area though where GPUs have really shined has been has been usability, as in uh, for like let's say you want to deploy like a PyTorch eager mode model, uh, it just works, right? Like it just works. Whereas like I've had personal examples, like let's say I don't know, using a TPU where okay, well, floating point 16 wasn't supported. Well, so it was just like super. It was just super slow without telling me. Or actually, no. So that was Jack's constraint. So basically, floating point 16 wasn't supported on Jack's CPU, and instead of just telling me that, it just like was super slow. So this is the kind of stuff to keep in mind. Like sometimes the hardware will force you to change the way you do your code, but ultimately the sort of holy grail is to say, well, I don't want to think too much about how the hardware is done. Ultimately, maybe that's something more the compiler people can think about. And maybe I can just be aware of a few tricks, like let's say increasing the batch size is one that like a lot of us know at this point. So basically, yeah. So, and I guess like a last point is really like when we talk about flops, right? So this is proportional to the number of transistors that you have, right? That you can fit on the machine itself. And this in of itself is also a function of the price of a transistor. So this is a bit counterintuitive, right? Because you would generally think of like, well, this thing is better from an engineering standpoint or whatever. But this matters. Like if you, let's say, like if I were to go create like some sort of new hardware, and I would have to go call up my contacts at TSMC, which I don't have any, and I'd be like, look, I have this like new hardware that I want to work on. They would charge me like a huge premium because I don't have like economies of scale. I don't have volume. They don't know me, so there's like a risk attached to it. Whereas like with Nvidia, they know exactly. Like they have a long-standing partnership. They probably like have like they meet every day. All sorts of PMs and devs working with each other. It's all good. But this also influences the price, right? Like if you have a good relationship with someone, you're more likely to offer them like discounts on the price or premium service or more tricks on how to use the hardware better. So all these things really matter because then when you're comparing hardware, the way they do it is that they say there's a comparison called the total cost of ownership. So this is basically the price of the item amortized over time. But another way to think about it is to say something like, throughput by dollar, right? So if your machine, like let's say, gives you 1,000 images per second, but mine gives you 100, but it's 100 times cheaper, my machine is actually better, right? And now, is it 100 times cheaper because I'm literally losing money? I'm just like burning my own savings, or is it because I negotiated a better price, or because I have a better architecture? Whatever it is, like even throughput per dollars is a metric that can be fairly deceiving. You sort of need to peer a bit under the hood, right? Because if someone let's say you do offer a good compelling throughput per dollar, potentially what the company like Nvidia could do is just say, okay, great, like you're a threat, like let me slash prices by 10, and like, okay, go F yourself, right? Like there's just like not much you could do to like for something like that. So just something to consider, like when comparing hardware. These are all things you should think about, like the application, the actual hardware spec, the architecture to some extent, but I think what really matters is actually the number of transistors and the price, like a lot more than the architecture. So this is something we'll come to back in a second. So yeah, so basically here, like, so most of the designs here is like there's a couple in China, but I would say most of this is US, right? And then for mining, this is mostly China. And then this is, I think, also mostly China. This is probably more US. And then this is Taiwan. All right. So this is TSMC. So TSMC is interesting because it's probably the single most valuable company on the planet. And it's probably a company that a lot of people have never heard of, right? Like people in software maybe, but it's just like not a company that you see like commercials about or have people think about, like, joining internships there or something, right? But the thing to keep in mind is that, like, well, also the growth of the company has been explosive. And pretty much, like, so what they pioneered was sort of an interesting approach. Like historically, companies that do like, oh yeah, and then there's maybe it's just like technology, like other manufacturing. So this is manufacturing of the chips themselves, but there's manufacturing technologies and materials. So so you're gonna have like Applied Materials. It's a company that builds like semiconducting materials, right? So there's a lot of research that goes into there. Like, how do you make sure that it's very conductive, that doesn't dissipate too much heat? This is all hard science stuff and quantum stuff, like very fancy stuff. But then there's also companies in the Netherlands that do EUV, like electron. Let's see, what was it called again? EUV technology. What was the company called? Yeah, ASML Holdings. Yeah. So ASML also is like another company that provides a technology so that you can use light to etch circuits. So right when you see a circuit, it sort of looks like, it's like this maze thing. So humans obviously can't do these, so you use like these light lasers to etch them. So ASML is sort of the pioneer to EUV technology. This is ASML, right? And so even though what you may have noticed was there's definitely a lot of influence in the space centered around China and the US. Then there's a bunch of European companies. And then there's TSMC that's sort of, very like too close to China for the US to be comfortable, but at the same time existentially important for both companies. So again, TSMC probably the single most important company on the planet, in my opinion. That doesn't mean it like okay. So when I say it's the single most important company on the planet, I don't mean that it's this company that makes the most money on the planet. What I'm saying is that is if you sort of magically remove this company from the planet, you would probably have the most repercussions out of any other company. Probably, I need to think. Maybe some economists would need to help me think through this argument. But at a high level, this is why I'm saying it's such an important company. And software, like this is really what we're talking about. Like, well, there's people building a software stack on top of these accelerators, right? So you have stuff like PyTorch, but also the lower level layers, like you have stuff like NumPy or the BLAS library. So sort of the ecosystem on top of it. This tends to be open source, but not everything, right? Like CUDA isn't. Uh, like Intel's MKL isn't. So if it's valuable enough, I think it tends to not be open source at least. Uh, so one of the reasons why TSMC became so big and it basically manufactures like most chips on the planet today from most companies is because they pioneered what's called the fabless model. So the fabless model basically means that you don't sell GPUs, but you partner with companies that need to create GPUs and you sort of like promise that you're not going to steal their designs. Right. And if this sounds a bit weird to you, it should, because like, why would you trust them? And right. And so it just takes a single breach of trust. As in, like, let's say, I don't know, like TSMC CEO gets pressured to share some docs with some country from another country, like let's say the Chinese designs to the US or US designs to China. And you can see why very quickly people would be very reluctant to trust TSMC. And this is why like their reputation has been, I'd say, really stellar among at least I think for Nvidia, at least they have a good partnership. So there's no reason, or at least not no reason. There would be very strong reasons for them to sort of breach the trust there. So there's this article I really loved. It's by this website called Foreign Policy. I'd never heard of it, but it gives you a good visualization of the whole space, right? And so it talks about, well, you have the raw material sourcing. Then you have like R&D, basically people that come up with interesting technologies for how to build semiconductors. So, like the researchers could be academics as well. And, there's it could also be companies that could license their IP. And then in production, we sort of split into two. Historically, companies like Intel, for example, do what's called like integrated device manufacturing, as in it means they do everything. Like they design their chips, they manufacture it, they build the software for it, like they do everything. And this sort of fell out of favor with the fabless model, like which seems to actually be doing a lot better, where companies like Qualcomm, Broadcom, Nvidia, AMD will design their chips, but then they'll be manufactured by TSMC or some other companies, usually in South Korea and Taiwan. And then when it gets assembled and tested, mostly also places in Southeast Asia. Actually, mostly, I shouldn't say that, mostly Taiwan, one in China, and then one in the US. And then, okay, I forgot about distribution as well. But basically, just like whether it's like returning, repairing, so sort of the supply chain, more like the Amazons of the semiconductor business with packaging. How do you put this in circuit boards? How do you make this easy to use? Like if you're eventually buying an Arduino or something, right? That's sort of a higher level module. So, and again, all of these are extremely capital intensive. Probably all require lots of government subsidies to work out, or so it's one of those areas where actually I feel a lot of free market ideology just doesn't really hold, because at least within the US, like as far as I can tell, like the US government doesn't necessarily invest all that much in semiconductor industry. I think Intel is trying to change this now and getting some grants for building stuff locally and stuff. But again, it's going to take forever because like this is not software, right? Like you don't just like go in your room and then, hack a bunch and then a year later or maybe a couple of weeks later you have like some prototype that's better than everything. Like you actually need to set up the factories, you need to train workers that need to learn how to build it. It needs to be safe. You need to slowly improve it. And it's just really hard if you're not like borrowing what you're learning from other countries. Which is why actually, like for example, like I was reading recently that Samsung would have like a big foundry in the US. I believe it was Texas. I could be wrong. But the idea there is that they would get tax breaks. In return, they would basically teach American workers how to build chips. And sort of like one theme here is that especially after COVID happened and sort of global supply chains went haywire, it became sort of existentially important for countries to have a bit more control over their full hardware stack. And so basically this over dependence on TSMC has become a weakness, even though sort of in peacetime it was a real strength, right? And so this is how you should think a bit, I think, about globalization, where in peacetime it's great because it allows specializations, it allows economies of scale, broad partnerships. but it adds a sort of a fragile point to your manufacturing where, well, what if Taiwan doesn't want to work with us one day, or like what if, like, whatever happens, like what if the CEO dies, like, it could just be the most random stuff, and then all of a sudden, like, the world changes in extremely complex ways, right? So this is sort of the cautionary tale there. So here, like most of the silicon production we saw here, it's China. So, but this just sort of puts it in perspective. Like, look at the gallium, like 97%, right? Like, it's just not even close. So for R&D, it looks like the US leads the way, but not by sort of these large margins, and then the European Union. Intel spends the most because it's also the largest, right? And so I think what's interesting about Intel's chips, maybe it was a mistake for them not to go into the graphics and deep learning space. I don't know the history as to why they didn't do it. And then when you think of other companies like Qualcomm and Broadcom, like, well, either they're thinking about building chips that work really well on phones. Uh, so Qualcomm really, a lot of their money is really propped up by Apple, but I believe Apple recently negotiated a contract with a Chinese company instead. So again, that's a huge blow. And I don't think they did it for political reasons. It was just because the Chinese tech was actually better. Uh, and so this is just, like, again, another thing to keep in mind, where, like, these are huge businesses, but they're heavily centralized. Like, Apple just has so much weight in the business, and they want to make their, like, phones so thin every year that the quality of your chips really matters. And, like, they have to be really thin, they have to dissipate heat well. It's all things that are super complicated. Um, yeah. So here, for example, you're seeing, like, so these are integrated circuit design companies. So this is just in general R&D. Uh, so no surprises here in the names, right? Like MediaTek, you may have not heard of, but Xilinx also builds stuff. Like Novatech, I don't know too much about, but just something to keep in mind here. Like, these companies are all pretty much household names at this point. So in terms of, like, so ASML I mentioned, right? So this is the EUV company, like, where you use laser etching. It's sort of really interesting. So maybe I should just show you this, like, EUV tour YouTube, just so you can get a sense of what this actually is, right? Um, so when we talk about these kinds of places, it's not like, oh, it's like a machine. It's like, look at, like these guys are, like, sitting, like, in these labs that are, like super advanced. Like, they're like really pushing the limits of physics and of, like, our knowledge of light. Here, like, let's see, like this, like people are like, they're wearing hazmat suits because, like, if you don't want it's cold in there, I believe. And also, like, if you have, like, a single hair anywhere, it could cause a short circuit. It can cause some impurities in the design, which then causes hardware to fail. So again, this is why, like, even if you do decide to build technologies like this, it's not like you can just go decide to do it. Like, I think we're fortunate in software where it's one of the rare fields where, even if you don't have too much domain expertise in something, you can just, like, YOLO and go do it, whether it's by no code or picking a simpler problem, or you just go talk to customers. But this is something where it's very clear what the customers are. Like, they're very big, and what they want is, like, much thinner, like, they want much thinner transistors, so that you can fit a lot more of them and get more flops out, right? Because the more flops you can do, the more interesting algorithms you can run. And specifically for a lot of these newer algorithms in deep learning, they're all very flops intensive. And so the companies to crack this, it's a big deal. And so again, like, this is why Nvidia has become just such an important company. Uh, you know, Debatable whether it's the second most important company in the world after TSMC at this point. Probably not, actually, but just something to keep in mind. All right. And so back to here, manufacturing. Let's see. Okay. So testing and packaging also mostly in Taiwan. There's one in US, one in China, but it really feels like Taiwan is sort of the epicenter of a lot of this stuff. And just to put this in, okay, but sales is sort of interesting, right? And this is sort of like another, like another aspect where, even if you manufacture the core technology, what really matters is, like, are you the one making money off of it? So who do your customers interact with? And so, for example, here, like, we're probably not gonna see TSMC, right? Because, like, they don't. Oh, no, they are here. Sorry. So, but they're number three, even though they produce most of the chips. And I guess, like, well, really realistically, like, Intel is still sort of the market leader, right? And Samsung and their phones as well, and their full stack, right? Like, they can build their own hardware, but also, where's ASML? ASML. Let's see. ASML showed up like in yeah, why is it not showing up here in sales? I guess like they just don't show up here. Or like they don't trade in semiconductors directly, right? Like they trade in the technology to produce it. All right. So this has been, I guess, like a big overview. And I will say that if you are interested in learning more about this blog that I shared here. Wait, did I remove it? I need to save this blog because it's amazing. I was looking for it for like 10 minutes today. So this article is incredible. Like I would recommend anyone in technology read this thing. It'll really blow your mind and show you just how complicated stuff are. Other Substacks that I would really recommend is Deep into the Forest. That's why I said forest by Barath. So Bharat recently started to talk a lot more just in general about deep technology, but like my favorite articles of his are his earlier articles on semiconductors. I would say a lot of the best ones. Yes, I will share all the links in the description after this. So yeah, happy to do so. Let me just quickly bookmark it. So well, like what I really liked about his earlier articles is he went quite a bit into like electronic design automation tools, or like let's say where is it here? So how do you manufacture solar cells? Also, solar cells is kind of interesting because I think to produce them you need petroleum, and then also like a lot of the material, like for lithium, you need to mine it. So it's not like like it's not like you're planting a leaf or something and then it's collecting energy. It's still like a fairly like industrialized process. Regardless, um, and then the second Substack I'd really recommend is Semi Analysis. So this one, I was reading about like, so I'd heard about Dylan for a while now, but this article blew my mind, and it gives you some sense of some of these geopolitical tensions. So this was ARM, right? So ARM had like sort of had a Chinese branch, and then ARM in the West wanted to fire the CEO, and the board sort of unanimously agreed to fire him. But instead, the guy actually so despite a 7-1 vote by the ARM China board, the company's seal was still held by Alan Wu, and the seal is a stamp which authorizes that the person in possession to bind the company with rights and obligations. And then they tried to like sue him to get the seal. But despite being formally fired, and this is where this gets really crazy, Alan Wu has remained in power. He ousted executives that were loyal to ARM. He has even hired security paid for by ARM China that reports to him. So he literally hired people to be like, throw people out of the building, like physically. And this has security has kept ARM out of the China offices. So he basically did a coup, and he started his own. He renamed the company. Uh, I mean, if someone can read Mandarin, please let me know what this company name is, because I couldn't read it. I think it was this. Um, but regardless, like it's just something to think about, right? Like where this is kind of crazy, right? Like you have like a huge company with tremendous value, tremendous like domain knowledge and designs and expertise and contacts, and then like the CEO can just go rogue. And this is where like a lot of the stuff becomes a natural security concern for the states, because if they don't build a good solution for this, and a lot of the manufacturing doesn't happen in the US, this can potentially mean that the US is either sort of in the worst case, like limiting the number of available computers, or in the best case, using technology that's like 5 years old, depending on when Intel manages to build their new like foundries, which takes a long time, right? Like I said many times, this is the world of it's the physical world. It's not the world of bits. Um, so that said, like, don't take any of this that I'm talking about as sort of investment advice, because like even Nvidia like grew insane in 2018. It was around the time of the crypto like boom and then bust of 2017. You can sort of see how this correlates. It crashed. Like people lost more than like 2/3 of their money. That's it. They made most of it back. So some stuff also doesn't make too much sense. Like basically after the stock split. So this is a Tesla chart, but the Nvidia one looks very similar. So the stock split is basically saying, well, the individual stock price is too expensive, so we'll just basically pretend like every stock is 5, and that makes it easier for people to buy it. And then because it goes down in value, people are more likely to actually purchase it. And so then the stock increases even more, detached from sort of its fundamental value. Like, I mean, like it becomes like, like this is sort of a longer point. Like sort of everything is becoming a meme nowadays. It's very hard to figure out like what has value and what doesn't. But just something to keep in mind. Like, I mean, just be skeptical, just do your own research and stuff. So one thing I also thought was interesting was like recently, because of shortages, TSMC has announced that they're going to increase their prices by about 20%. And so you would expect that, well, eventually, if the prices increase too much, then maybe other competitors, like maybe their partners aren't going to be as willing to work with them, and it puts a cap on their growth, and so their margins go down, and as a result, like the company's overvalued, and it's going to go down in value. But I don't think that's going to be the case. Like, and I think this article actually also makes that point where even if the margins increase, like this is just a sign that people really want these things, right? Like if crypto, deep learning, and gaming, like just one of them keeps growing, like maybe the gaming one matters a bit less than the other two. Uh, don't get me wrong, I love gaming. I just say it's again from the total number of people that can game versus the total number of cryptocurrencies that you can have and their total theoretical infinite value or whatever. So there's an upper bound. Uh, and also, like once you get to the limit of Moore's law, which we are reaching, like although Intel, like TSMC has been pretty close at reaching it, like basic number of transistors doubling. The fact that now like we're sort of hitting the limits doesn't mean that like we're sort of hitting the limit when it comes to fitting stuff on a single like 2D die. But like let's see, so 3D die. Let me show this to you. Okay, these are really lame pictures. Goddamn. Okay, so the idea with 3D die is that like ultimately there's sort of a limit on how many you can fit, and so you start basically putting them in 3D, right? And then the problem there, and I'm not an expert, is that well at 3D, like the heating becomes even more of an issue. But as long as you can do it, that means that you can fit more per like basically area, like cubic area. And so you can fit more. That means they're faster, they're smaller, and that's great. And so here you can see, for example, like where was Apple? Yes, so I remember it was here somewhere. I lost it now, but again, so this is like the idea here was that like Apple's really targeting like millimeter, like like maybe sub centimeter long. It's probably already like sub centimeter actually at this point. But like whatever millimeters they're going for, chip manufacturers have to be really accommodating, right? So they can just like literally set like these targets and say like, look, you need to meet this target, and then people like bust their heads. 5 millimeters. Oh, 5 nanometers. Yeah, yeah. So I think you're talking about the actual transistor. Yeah, yeah. So I was trying to remember what was the actual thickness of the newer iPhones going to be, like the iPhone 14 or something. I think I remember something like 7.6 millimeters, but that sounds ridiculous, actually. Probably, yeah, that does sound ridiculous. I forget what the number was. It was somewhere here. Anyway, um, so I guess like one last thing we can talk about, right? And so I briefly talked before on the stream about GPUs, right? And so in GPUs, typically you have a large on-device memory, not as large as RAM, but large. Let's say you have 80 gigs on the A100s. You have a relatively high memory bandwidth so that you can fully utilize the GPU. And then you have a very high number of flops per second with these floating point units. So they have like FP32, they have FP16 as well. And so both of those, like, so these are all like ALUs that are added. And then also just like some facilities to do this in a multi-processing way with streaming multi. So basically each streaming multiprocessor will have like a bunch of floating point units, and each of those floating point units can do a certain number of flops. All of these things can happen totally in parallel, with each part of the layer having a different set of caches, whether it's a cache relative to the thread or the streaming multiprocessor or something that's on the whole device. So caches are generally good for performance. Like it sort of makes sense. It's a very common trick. And the other trick is I/O, right? So here, for example, they're talking about, okay, well, we're doing this many teraflops of BF flow. 16, and then 22 teraflops of FP32. And then the on-chip bandwidth is 10 terabyte per direction. So I guess they have 4 directions. And the idea here is that, like, so NVIDIA, for example, has a technology called NVLink, which makes it faster for you if you want to scale models, that you could have the different GPUs talking to each other directly, as opposed to talking through the CPU or through RAM, right? So so typically that's done via PCIe Express. But if they can talk directly to each other, like, that's probably the future, right? Like, there's no reason to talk back to main memory. So they're doing something similar. And this answers the, well, how do you scale out, right? Like, I mean, this is fine for a single model. But what do you do for a very large model? And actually, this is a pretty big issue here, because I think their on-device memory for a single chip was just 1.5 gigs, which means that, like, if you're training large, BERT itself, I remember it was like 600 megs or something. And BERT's like a pretty small model at this point. Like, people have figured out like all sorts of ways to distill it, to make it smaller, to make it work. But that's not the trend that's not really the trend. Like, I think all signs are pointing towards larger models actually being like very economical. Economical as in, like, the performance really justifies it, right? Like they are a lot better on the end level task. And so the idea is that, so you basically do this. So essentially, like, one way, so they're saying, okay, well, our on-device memory is really small, and we're gonna manage to basically send a lot of data into the chip for what's basically actually like a mind-boggling, like 8 terabytes per second IO, right? So essentially, like, you could load like 8 terabytes worth of input data per second. So, theoretically, you could have an 8 terabyte sized, batch, and just do that whole operation in a single second. Um, few applications would use that, like, but definitely the ones that are more vision focused. Like, let's say you want to deal with high resolution images for self-driving cars or a robot or whatever. Those would use it, right? Because it's a video stream. Like, video gets pretty big. And so, one, you want to load this video on the chip really fast, and then also load it out. And then if you're doing some modeling with it, you want to make sure that the interconnect between the chips is very fast. So actually, like the author also correctly points out that, like, GraphCore also has like a similar issue with not having enough SRAM. So I believe last I checked, they had like 900 megs. It's probably more now. But this is just something to keep in mind, where basically a small SRAM generally means that it'll be faster if you can get things to fit. But the trend is towards larger models. So how do you get things to fit? Well, the tricks I've talked a billion times about on this channel, like model parallelism and pipeline parallelism. So, and other fancy ones like what's it called? Like no backprop methods. Right? So the software stack is what you would expect. So here they're saying, for example, well, we have a neural net model, and then we have a PyTorch model, and then we JIT it, and we have our own backend, right? So typically, a lot of times, like, these kinds of accelerators won't deal well with dynamic models, as in models that change. So models with if conditions and for loops and stuff. Those are generally not great for hardware accelerators. And so typically, you want to have a way to turn this into like, you want to basically compile this down into something that doesn't change. So there's a few popular choices, like whether it's StoreScript, Onyx, or whether they want to build their own. LLVM is interesting because there was this other effort with MLIR that is also like an LLVM based ML compiler. And what that does, and like, basically, you can think of like a lot of the tricks. I have a whole other video about ML compilers. But the tricks there are things like, operator fusing. So if you have sequential, like, reads, like if you have something that's like a load, so something that's like basically save op. Well, maybe you don't need to save it, right? You can just do the op 2 times in a row and save yourself talking back to RAM. So this is called operator fusing. Other stuff could be like, well, optimizing away loops. So basically, this is another very common like loop unrolling and loop fusion. So all the basic ML compiler tricks, and I have actually a GitHub repo that's pretty popular just on this, that goes over a bunch of tricks in C. But a lot of the same ideas apply in deep learning, right? So it's just thinking about, like, where is the paradigm different? Where is most of the value? Right? So it doesn't say too much more, I will say, about like the problems, but the main basically the main problem here will be that, and one thing I want you to keep in mind is that a lot of times in these fields, I think there's a lot of benchmarking that happens where people will give you, like, let's go back to our original picture here. Like, people will give you flops and then they'll give you memory bandwidth and then they won't give you this, right? But what you really care about is this. Like, this is ultimately what matters to an extent, because most hardwares are not, like, you can't compare them one to one. They're going to have different architectures, different number of transistors. So maybe a combination of looking at this and then throughput per dollar and then the price that they negotiated. Like, I actually, like, screw that. Like, you need to kind of look a bit at everything to sort of evaluate for sure whether a hardware is good or not. But for me, I think the number one rule is, if I can't SSH into it and run the benchmark myself, then how do I really know that the benchmark is accurate or not, right? Like, so one, there's sort of deliberate benchmarking, which is deliberately picking configurations that make your hardware look better than your competitors. So that's benchmarking. But then there could also just be like, more simple, more Lindy incompetence, right? As in, you don't know that you're benchmarking things incorrectly because maybe you're using your competitor's hardware incorrectly. Maybe you picked an algorithm that no one really cares about, but you're saying is really important. So these are all tricks to keep in mind, right? So hopefully, I hope you enjoyed this. I think this was a fun stream for me. So Hawkmonk is asking, like, what about new models that would be enabled by the hardware? Can't really benchmark that. You're exactly right, right? So in machine learning, at least, there's been this trend towards uh, like benchmarking. Yeah, like, I think it's probably, benchmark is probably going to be the title of my next blog post at this point. I've had a few people comment that they like it. Uh, so okay, so back to Hawkmonk's question, and please, guys, like to start putting questions in chat, because I do want to start wrapping up, but I'm happy to hang around. Um, so as far as like models that can't be, like, that you can't really run on existing hardware, I think in my view, this needs to be defined a bit more thoroughly. As in, are there generally algorithms that people care about that really suck on existing hardware? And if so, which ones, right? So there's a few candidates, I think, for some algorithms that just don't run very well. So there's stuff like scientific computing, like differential ODE solvers, probabilistic computing. So can you build hardware that solves those problems really well? And if not, then you really just need really good performance on BERT and ResNet, right? And so, and even like, let's say, forget BERT and ResNet for a second. Like, let's say BERT, like BERT is for the most part a dense model. GPUs don't really deal well with dynamic sparsity, as in, like, let's say you have just random elements that are zeroed out. GPUs don't necessarily take too much advantage of that. They take advantage of static sparsity, as in, I'm going to pick a pattern, like, okay, I'm going to zero out every other column, and then, like, shrink the matrix by like removing those things and doing some smart stuff with the striding and stuff like that. Like, structured sparsity is all fine and good, but that's not actually the nature of a lot of problems. Like, let's say you look at something like graph neural networks. Like, graph neural networks aren't statically sparse, they're dynamically sparse because it depends on who your neighbors are, right? Like, you have an adjacency graph that represents a graph. And you don't know which nodes a node is connected to. You have no idea, like, a priori. So making assumptions about it feels really silly. So same for probabilistic computing. Like, it's one of those things where people and statisticians have been using these tools for a long time. They've been used, I think, for maybe at least like 80 to 100 years, maybe more at this point. But they've definitely not penetrated industry, I think, in any sort of meaningful way. Like, sure, there's people doing Bayesian stuff, but I've never seen it get to a point that, let's say, solves model interpretability problems or solves like model bias problems. So these are sort of the problems that people hope will be really solved by these kinds of algorithms. So if you can solve them, great. But if you can't, you better bring BERT benchmarks. Yeah, thank you so much, I Infinity. Appreciate it. But yeah, I mean, like I said, if you have any other questions, feel free to drop them in the Discord. Okay, sure. Like, I'm going to take one more question. So Hawkmonk is asking, Kind of off topic, but imagine a world that has implemented the simulation for every process in the world, from constructing a house to building semiconductor chips. The knowledge would be executed by software instead by a human, and models for simulation would be open source, and maybe even some implementations. Do you think this would lower the barrier to entry to start a hardware business? You would need to acquire the domain knowledge, but it would be an advantage. You just need to know how to use the software, and the software is easy to use based on known convention and some money. Okay, great. I actually have a very simple answer to this question. So the chip placement problem. Uh, so the idea there is like, let's say you're building some sort of circuit, and you need to basically place chips on it. And the problem you're optimizing for is you want to make sure that the chip is as fast as possible. And that basically means that components that need to communicate frequently with each other need to be physically close to each other, right? Because there's a limit on the speed of light. So that adds like a hard limit to how fast things can get. And then the second problem is you want to make sure that the heat dissipation is manageable, right? So there was an effort at Google to do this via an RL approach, as in they used an RL algorithm and it built these very funky looking like chip designs, and turns out they were actually a lot more efficient and stuff. But then there's a couple of challenges, right? Like, well, because they're not sort of using these sort of standard grid shapes, they're actually much harder to manufacture. So even if theoretically you could construct it, it's just not economically feasible. And it's like one of those things that feels like it's only better in simulation, but not necessarily in the real world. You could make the case that better tools, so like let's say if I think of stuff like the Zachtronics games, like they build simulations for stuff. Like you can build like chips, you can build code for chips, and it's kind of interesting. Like you get to see, you get build gears, like all sorts of stuff, and it gives you an idea and a very strong intuition for how you could perhaps build stuff. But none of this matters like unless you can physically produce it in the real world, right? So again, this is not, I think, this is not a problem that's solvable by software. Design is maybe solvable by software, but manufacturing isn't, mining isn't, packaging isn't. Testing, maybe, like you could test a bit more in software, have designs that are a bit more robust. But I think the ones that are very important are, again, manufacturing and mining and testing. And especially with manufacturing and mining, it like that's kind of a lottery, right? Like if you're born, like let's say you're born outside of China, then like you probably don't get into the gallium business. Like it just doesn't make sense, right? Like there's 98% of it is there, so there's a hard also geographical constraint on where you need to be to start a successful business in the area. uh, so again, so we have a couple of people on the Discord channel on Robot Overlords that have some ideas for how to build better electronic design tools. And actually, most of the interesting electronic design tools are built either in so of course there's some in China and Taiwan, but a couple of them are in the US and in the European Union. Um, so yeah, like I said, I'm skeptical that this is a purely solvable problem by software. And a lot of problems are like that, even like energy grids. Like software can make like energy allocation more efficient, like bidding more efficient. Software doesn't let you actually put poles on the ground and connect wires to them and build nuclear reactors. Software doesn't let you build sewage systems. You need to go dig there. You can't build roads. Uh, so actually, there's a book I really love that I'd really recommend a lot of you check out. Uh, so let me bust it out. Where is it? So this book was absolutely gorgeous. No, so it was Infrastructure, I believe. Yeah, this book is amazing, guys. So it's called Infrastructure: A Guide to the Industrial Landscape, and it goes over everything from like how do you build like cars and planes and bridges and sewage systems and energy. And it's a gorgeous book. It's extremely illustrated, so you don't need to see. It's not a book that you read in a single sitting. It's a coffee book, so you just can sort of like open it up and peer through. And you're like, oh, like that's interesting. Like, like just how come sewage treatment plants are always like near the ocean? That's something important to think about. It's not just about like, maybe in countries like Lebanon, they'll just dump it in the ocean. But it's also because you want it to be in a low area so that when you're pumping like dirty water to it, just gravity makes it fall there. So there's all sorts of stuff you can think about here from like, but like I think hard science, that's actually one of the reasons why I like Bharat's Substack. on hard science is that this is not uh, these are not easy problems, right? Like these plants take a long time to build. That said, if you asked me, like, should you have been a nuclear energy, nuclear engineer, I'd have said probably no. Should you be a mechanical engineer? Probably no. I still think software is by far the highest leverage skill set you can have in engineering. There's a couple of reasons for that. Like, one is software has less regulation, as in you don't need to get permission from the government to deploy something to GitHub, but you do need to get permission from the government to deploy a small power plant. And also, it's much more capital intensive, so you need a lot more people involved. And that drastically reduces the scale of innovation. That said, not everything's a software problem, right? Like, Amazon is valuable because it has like amazing software to figure out how to connect vendors and buyers. It has a global logistics network. It has like factories where they can, not so, like base shipping plants where they can allocate uh, they can ship goods efficiently and route them efficiently. But the reason why Amazon is a very valuable business is because it actually has like a distribution network. Like, it's sort of like if Amazon wanted to turn into like, I don't know, like send like weapons to some to the U.S. government, like they'd probably be the most efficient at it. Like, let's say you wanted to do mail-in votes, like Amazon would probably be the fastest company in the world to ship like mail to everyone in the world. So that's something I think that people forget, and that software is high leverage, but the moats, like data is a moat in some sense, and I've talked about this a bunch. Some of you may have seen some of my comments around supervised learning, where if you do if you have a product that's useful and that collects data that makes it better automatically, that is a moat, and it's very difficult to compete against, like Google search. That said, the physical world is also a moat. So if you went through the regulation to build a nuclear power plant, and you have the engineers and you have the expertise, and you like look at like San Diego Gas and Electric, right? Like, so they like they, like if they increase prices, like I just have to pay it. Like, it's just like that's it. There's just San Diego Gas and Electric. So same for railway companies, right? So that's why historically, even like, maybe I'm gonna sound a bit like a conspiracy theorist, but like if you look at people like Bill Gates, for example, Bill Gates is actually the largest owner of farmland in the world. So you would expect Bill Gates to only be investing in tech startups. That's not true. And actually, I think people like him that have that much money recognize the benefits that owning real assets in the real world brings. So whether that's land, with traditional real estate and cities that's scarce, whether that's farmland, also scarce. Like, there's only so much land you can have. Like, we can't build stuff in the sky, like not yet, at least not for a couple of. I'm not optimistic. Like, we'll get to be interplanetary anytime soon. Uh, I think I'll just take too long. But again, the real world is something that needs to be respected, and I hope learning a bit more about semiconductors give you some of this perspective as to the complexity of this space. All right, we're at the 1 hour mark. If someone wants to humor me, ask me another question. I'd be very happy to answer them. Yeah, Hawkmonk, I'm more than happy to do. Though those are great questions, so I enjoyed answering them. Um, And yeah, I think that's it for me, folks. Thank you so much. I will put this video later on YouTube today. I will also put the links in the description. And if you want to discuss this even more with me, feel free to ask me questions on the Robot Overlords Discord or just in the YouTube chat. More than happy to. And yeah, and I will say, like, I am thinking a bit more about what my next Substack article should be. Like, work has been very hectic, so I apologize for my slower pace there. But I have a couple of ideas. Whether I have a couple of, maybe I'll just give you the titles and you let me know what sounds interesting. So one is benchmarking. The other is like the working man's guide to deep learning. Uh, and then the other is the Wanker manifesto. So let me know what sounds more interesting in the comments section below. I'm not going to give you more detail than that. But you can guess. Like, I guess if you were to look at my tweets carefully, you can get a pretty good guess as to what those blog posts will be about. As always, guys, like, thank you so much. I really enjoyed this. And if you have any feedback or content suggestions, like I said, feel free to let me know. Always happy to take them. Thank you.